Welcome, Hornets, and thank you for participating today and listening to my video. We're going to be talking about the second comparison test today, called the limit comparison test. The limit comparison test could be thought of as the L'Hopital's comparison test because we're going to be taking a look at a limit of a ratio of two series. So two rules, basically, an A sub n and a B sub n. Now, one of these series we are going to make that we will already know will either converge or diverge. That's important to know because as we do this ratio and we simplify it and take our limit to infinity, if we get a positive finite value, both series do the same thing. So if I choose uh, a converging series to compare with, and I get from my ratio's limit a positive finite value, then both series will converge. If I choose um, a diverging series to compare with, then after my ratio, if I end up getting a positive finite value, then I know that both will diverge. This is what the limit comparison test does. And because it doesn't require us to find a specific series that is smaller or larger than the one we're comparing, it is considered a more powerful or stronger theorem. It's a stronger test. So the direct comparison test, although useful for some, is not useful for all of them. In fact, it's less useful than we would like. So let's just take a look at the basic idea of the limit comparison test. Sorry about that, people. Here we go. So the limit comparison test, also known as LCT, is a stronger test. Let's go to our basic concept. Suppose that we have two series. A sub n is greater than 0 and B sub n is greater than 0. And we end up getting a limit. That is, the limit as n approaches infinity from the ratio of A sub n over B sub n. Then they both must do the same thing. If A sub n diverges, then B sub n will diverge. If A sub n converges, B sub n converges, and vice versa for B sub n to A sub n. So the way we work with this is we are going to be selecting a P series, just like we did before, but these are more complicated and they're not going to necessarily be a, quote, pure P series. All right? In fact, this is going to require us to work with something called a net P. A net P. We'll be talking about that in this video. Now, when choosing the series for comparison, you are going to disregard all but the highest power of n in both the numerator and the denominator. We're going to get rid of coefficients and we're going to get rid of sums of lower values of n. Problem is, we have to keep things that aren't involving a P series. Okay? Now, the process requires us to find the net P first. Then we find a semi-pure series, and you'll see in my first example what I mean with that, in order for us to compare with. And then we're going to construct the limit with the given series on top and our, quote, pure P series in the bottom, the semi-pure P series. We're then going to take the limit. As we take the limit, we may use L'Hopital's rule, we may use our ratios of leading coefficients, we may be using whatever we have to find that limit. That may mean we divide by the highest power of n for every single term. We did that at the beginning of last year. Let's take a look. Now remember, we do have one thing to be careful of. We have to get a positive finite value. And if we get 0 or positive or negative infinity, it means that one of the two series, okay, whichever one we've chosen, that semi-pure series that we're talking about from the net P that I'm about to show you, well, it means that one of the two series is growing faster than the other. In fact, it's growing too fast. And because it's growing too fast, it's throwing everything off. So when you get 0 or positive or negative infinity, you need to stop doing the limit comparison test. It's the wrong test. It's never going to work. Go to a new test, find a new way. All right, so please just be aware of that. All right, how do we find a net p? Let's look at that first. Let's take a look at n squared over 5n to the 5th plus 7n. So if I were working with this summation as n starts from 1 to infinity, the pure p series that I'm looking at is only working with the highest powers of n in the numerator and the denominator. So the net p here is going to end up being 1 over n cubed. And that would be the value that we're going to try to work with. Now be aware that certain series aren't always going to get rid of everything we want. For example, I might have some exponential or logarithmic or geometric or something that's there. Okay, could even be factorial. When that happens, we end up keeping those pieces and they become part of our limits. So let's look at what we're going to have to do. All right, so if I were working with this one, I would immediately set up my limit as n approaches infinity, and I'm going to put my n squared over 5n to the 5th plus 7n and 1 over n cubed. Now, we know that this simplifies. For example, let's just simplify it, see what happens. We're going to get n to the 5th over 5n to the 5th plus 7n. Now, it's at this point I can use L'Hopital's rule. I'm going to have to use it 5 times. I can look at the ratio of leading coefficients, or I could even divide. For example, n to the 5th divided by n to the 5th, 5n to the 5th over, whoops, that went to a power, 5n to the 5th over n to the 5th plus 7n over n to the 5th. You might recall this from your first semester last year. Just make sure we put our limit statement in front, and we're going to clean it up. We end up getting the limit as n approaches infinity, and I have 1 over 5 plus 7 over n to the 4th. This goes to 0, and I'm left with 1/5, a positive finite value. And because I have a positive finite value, because I selected a converging p-series, I know that the series that I'm looking at must also converge. This is by the limit comparison test. So by the limit comparison test, the summation as n goes from 1 to infinity for n squared over 5n to the 5th plus 7n must converge as the series summation n equaling 1 to infinity of 1 over n cubed. And that's my answer. Make sure you can see that, please. That way everybody can understand what I'm doing. I got a positive finite value, and therefore the series that I was testing has to converge with the pure p series that I'm looking at. Alrighty, that's the basic idea, and in the next video I'm going to do a couple of examples in an effort to try to help people understand. Thank you very much, and please have a very good and safe day. Be well, Hornets. Bye-bye.